Hello and welcome. My name is Alan. Sit down, get you something to drink, relax a bit. We're reading more ideas and opinions of Albert Einstein. We'll be getting into part 5 of the piece we've been reading. And part 5 is called Quantum Theory and the Fundamentals of Physics. The theoretical physicists of our generation are expecting the ejection of a new theoretical basis for physics which would make use of fundamental concepts greatly different from those of the field theory uh, considered up to now. The reason for it has been found necessary to use for the mathematical representation of the so-called quadrant phenomena, entirely new methods. While the failure of the classical mechanics is, as revealed by the theory of relativity, is connected with the finite speed of light, it's not being infinite. It was discovered at the beginning of the century that there were other kinds of inconsistencies between deductions from mechanics and experimental facts, which inconsistencies are connected with the finite magnitude. It's not being zero of Planck's constant h. In particular, while molecular mechanics requires that both heat content and monochromatic radiation density of solid bodies should decrease in proportion to the decreasing absolute temperature, experience has shown that they decrease much more rapidly than the absolute temperature. For a theoretical explanation of this behavior, it was necessary to assume that the energy of a mechanical system cannot assume arbitrary values, but only certain discrete values whose mathematical expressions were always dependent upon Planck's constant of h. Moreover, this conception was essential for the theory of the atom, Bohr's theory, for the transitions of these states into one another with or without emission or absorption of radiation. No causal laws could be given, but only statistical ones. And a similar conclusion holds for the radioactive decay of atoms. which is which was carefully investigated about the same time. For more than 2 decades, physicists tried vainly to find a uniform interpretation of this quantum character of systems and phenomena, such as such an attempt was successful about 10 years ago through the agency of two entirely different theoretical methods of attack. We owe one of those to Heisenberg and Dirac, and the other to Broglie and Schrodinger. The mathematical equivalence of the two methods was soon recognized by Schrodinger. I shall try here to sketch the line of thought of de Broglie and Schrodinger, which lies closer to the physicist's method of thinking, and shall accompany the description with certain general considerations. The question is first, how can we assign a discrete succession of energy values h to the power or hn to a system specified in the sense of classical mechanics and energy function is a given function of the coordinates qr and the corresponding moments pr. Planck's constant h relates the frequency h n divided by h to the energy values h to hn. It is therefore sufficient to assign to the system a succession of discrete frequency values. This reminds us of the fact that in acoustics, a series of discrete frequency values is coordinated in a linear partial differential equation or given boundary considerations, namely the sinusoidal periodic solutions. In corresponding manner, Schrodinger set himself the task of coordinating a partial differential equation for a scalar function I'm not sure the Greek letter to be given function uh, a Greek letter multiplied by QRS PR, where the QR is time t and where the QR and the time are independent variables. In this, he succeeded for a complex function, again the same Greek letter, in such a manner that the theoretical values of energy H V1 as required by the statistical theory actually resulted in a satisfactory manner from the periodic solutions of the equation. To be sure, it did not happen to be possible to associate a definite movement in the sense of mechanics of material points with a definite solution, Greek letter QR squared times T of the Schrodinger equation. This means that the Greek letter function does not determine, at any rate, exactly the story of the QR as functions of the time, t. According to Born, however, an interpretation of the physical meaning of the Greek letter functions was shown to be possible in the following manner. Greek letter, Greek letter, the square of the absolute value of the complex function, Greek letter, is the probability density of the point under consideration in the configuration space of the QR squared at the time t. It is therefore possible to characterize the content of the Schrodinger equation in a manner easy to be understood, but not quite accurate, as follows. It determines how the probability density of the statistical ensemble of systems varies in the configuration space with the time. Briefly, the Schrodinger equation determines the change of the function Greek letter of the QR with time. It must be mentioned that the results of this theory contain as limiting values the results of particle mechanics if the wavelengths encountered in the solution of the Schrodinger problem are everywhere so small that the potential energy varies by a practically infinitely small amount for a distance of one wavelength in the configuration space. Under these conditions, the following can in turn be shown. We choose a region G0 in configuration space, which, although large in every direction in relation to the wavelength, is small in relation to the relevant dimensions of the configuration space. Under these conditions, it is possible to choose a function Greek letter for the initial time t of 0 in such a manner that it vanishes outside the region G of 0 squared and behaves according to the Schrodinger equation in such a manner that it retains this property. Approximately, at least, also for a later time, but for the region G0, having passed by that time t into another region G. In this manner, one can with a certain degree of approximation speak of the motion of the region G as a whole, and one can approximate this motion by motion of a point in the configuration space. This motion then coincides with the motion which is required by the equations of classical mechanics. Experiments on interference made with particle rays have given a brilliant proof that the wave character of the phenomena of motion is assumed by uh, by the theory does really correspond to the facts. In addition to this, the theory acceded easily in demonstrating the statistical laws of the transition of a system from one quantum state to another under the action of external forces, which, from the standpoint of classical mechanics, appears as a miracle. The external forces were here represented by small time dependent additions in the potential energy. Now, while the classical mechanics while in classical mechanics such additions can produce only correspondingly small changes of the system, in the quantum mechanics they produce changes of any magnitude, however large, but with correspondingly small probability, a consequence in perfect harmony with experience. Even an understanding of the laws of radioactive decay, at least in broad outline, was provided by the theory. Probably never before has a theory been evolved which has given a key to the interpretation of the calculation of such a heterogeneous group of phenomena of experience uh, as has quantum theory. In spite of this, however, I believe that the theory is apt to beguile us into error in our search for a uniform basis of physics, because, in my belief, it is an incomplete repercussion or representation of real things, although it is the only one which can be built of the fundamental concepts of force and material points quantum corrections to classical mechanics. The incompleteness of the representation leads necessarily to the same statistical nature incompleteness of the laws. I will now give my reason for this opinion. I ask first, how far does the Greek letter function describe a real state of a mechanical system? Let us assume the Greek letter R to be periodic solutions put in the order of increasing energy values of the Schrodinger equation. I shall leave open for the time being the question of how far the individual Greek letter R are complete descriptions of physical states. A system is first in the state Greek letter square of lowest energy, stylized E2. Then, during a finite time of a small disturbing force acts upon the system. At a later instant, one obtains then from the Schrodinger equation, a Greek letter function of the form Greek letter equals sigma CR Greek letter R, where the CR are complex constants. If the Greek letter R are normalized when the true value of CR is nearly equal to 1, C2 etc. is small compared with 1. One may now ask, does Greek letter describe a real state with 1, or real state of the system? And if the answer is yes, then we can hardly do otherwise than ascribe to this state a definite energy, stylized E, and in particular an energy which exceeds stylized E1 by a small amount. In any case, stylized E1 is less than stylized E, which is less than stylized E2. Such an assumption is, however, at variance with the experiments on electron impact such as have been made by J. Franck and G. Hertz, if one takes into account Millikan's demonstration of the discrete nature of electricity. As a matter of fact, these experiments lead to the conclusion that energy values lying between the quantum values do not exist. From this, it follows that our function's Greek letter does not in any way describe a homogeneous state of the system, but represents rather a statistical description in which the C of CR represents probabilities of the individual energy values. It seems to be clear, therefore, that Born's statistical interpretation of quantum theory is the only possible one. The Greek letter function does not in any way describe a state which could be that of a single system. It relates rather to many systems, to an ensemble of systems, in the sense of statistical mechanics. It except for certain special cases, the Greek letter function furnishes only statistical data concerning measurable magnitudes. The reason lies not only in the fact that the operation of measuring introduces unknown elements, which can be grasped only statistically, but because of the state of one single system, the Schrodinger equation determines the time variations which are experienced by the ensemble of systems which may exist with or without external action on the single system, which such an interpretation eliminates also the paradox recently demonstrated by myself and two collaborators, and which relates to the following problem. Consider a mechanical system consisting of two partial systems, A and B, which interact with each other only during a limited time. Let the Greek letter function before their interaction be given. Then the Schrodinger equation will furnish the Greek letter function after the interaction has taken place. Let us now determine the physical state of the partial system A as completely as possible by measurements. Then quantum mechanics allows us to determine the Greek letter function of the partial system B from the measurements made and from the Greek letter function of the total system. The determination, however, gives a result which depends upon the physical quantities, observables of A, and have been measured, for instance, coordinates or momenta, since there can be only one physical state of B after the interaction, which cannot reasonably be considered to depend on the particular measurement we perform on the system A separated from B, it may be concluded that the Greek letter function is not unambiguously coordinated to the physical state. This coordination of several Greek letter functions to the same physical state of system B shows again that the Greek letter function cannot be interpreted as a complete description of a physical state of a single system. Here also is the coordination of the Greek letter function to an ensemble of systems eliminates every difficulty. The fact that quantum mechanics affords in such a simple manner statements concerning apparently discontinuous transitions from one state to another without actually giving a description of the specific process. This fact is connected with another, namely the fact that the theory in reality does not operate with the single system, but with a totality of systems. The coefficients CR of our first example are really altered very little under the action of the external force. With this interpretation of quantum mechanics, One can understand why this theory can easily account for the fact that weak disturbing forces are able to produce changes of any magnitude in the physical state of a system. Such disturbing forces produce, indeed, only correspondingly small changes of the statistical density of the ensemble of systems, and hence only infinitely weak changes of the Greek letter functions, the mathematical description of which offers far less difficulty than would be involved in our mathematical description of finite changes experienced by part of the singular systems. What happens to the single system remains, it is true, entirely unclarified by this mode of consideration. This enigmatic event is entirely eliminated from the description by the statistical approach. But now I ask, is there really any physicist who believes that we shall never get any insight into the important changes in the single systems, or their structure and their causal connections, regardless of the fact that these single events have been brought so close to us thanks to the marvelous inventions of the Wilson chamber and the Geiger counter? To believe this is logically possible without contradiction, but it is so very contrary to my scientific instinct that I cannot forego the search for a more complete conception. To these considerations, we should and add those of another kind, which also appear to indicate that the methods introduced by quantum mechanics are not likely to give a useful basis for the whole of physics. In the Schrodinger equation, absolute time and also the potential energy play a decisive role, while the two concepts have been recognized by the theory of relativity as inadmissible in principle. If one wishes to escape from the difficulty, he must found the theory upon field and field laws instead of upon forces of interaction. This leads us to apply the statistical methods of quantum mechanics to fields, that is, to systems of infinitely many degrees of freedom. Although the attempts so far, people are restricted to linear equations, which, as we know from the results of the general theory of relativity, are insufficient. Are the complications met up with now mainly, or with met up to now by the very ingenious attempts, are already terrifying. They certainly will multiply if one wishes to obey the requirements of the general theory of relativity, be the justification of which in principle nobody doubts. To be sure, it has been pointed out that the introduction of a space-time continuum may be considered as contrary to nature in view of the molecular structure of everything, which happens on a small scale. It is maintained that perhaps the success of the Heisenberg method points to a purely algebraical continuous or algebraical method of description of nature. That is, the elimination of continuous functions from physics. Then, however, we must also give up on principle the space-time continuum. It is conceivable that human ingenuity will someday find methods which will make it possible to proceed along such a path. At the present time, however, such a program looks like an attempt to breathe in empty space. There is no doubt that quantum mechanics has seized hold of a good deal of truth, and that it will be a touchstone for any future theoretical basis, in that it must be deducible as a limiting case from that basis, just as electronics is deducible from the Maxwell equation of the electromagnetic field, or as thermodynamics is deducible from the classical mechanics. However, I do not believe that quantum mechanics can serve as a starting point in the search for this basis, just as vice versa, one cannot or could not find thermodynamics, respectively statistical mechanics, the foundations of mechanics. In view of this situation, it seems to be entirely justifiable seriously to consider the question as to whether the basis of field physics cannot by any means be put into harmony with quantum phenomena. Is this not the only basis which, with that presently available mathematical tools, can be adapted to the requirements of the general theory of relativity? The belief prevailing among the physicists of today that such an attempt would be hopeless must have its root in the unwarranted assumption that such a theory must lead in first approximation to the equations of classical mechanics for the motion of uh, corpuscles, or at least two total differential equations. As a matter of fact, up to now we have never succeeded in a field theoretical description of corpuscles free of singularities, and we can a priori say nothing about the behavior of such entities. One thing, however, is certain. If a field theory results in a representation of corpuscles free of singularities, then the behavior of these corpuscles in time is determined solely by the differential equations of the field. That one was one of length, but yeah. Einstein talking a bit about how different theories work together in physics, and then goes into quantum physics itself. But yeah, let me see. I want to say that Greek letter was like a tau or something like that. Let's see. It is the Greek letter phi. Okay. Wait, no, it's not. It's not phi. It's psi. PSI. Excuse me. Let's see. I got sigma right. Yeah, I'm not someone who's real knowledgeable on the Greek alphabet. I never took Greek. Trying to see if we've got the stylized E. I think it's epsilon. Yeah, I thought it might have been, but I wasn't sure. But anyway. Yeah. This this has been a heck of a piece. But I appreciate y'all watching. Oh, as always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next video. Until then, later.